Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is concrete dome, tank, and shell modeling in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Paul Kilo will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Tiefenbach, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to quickly explain RFEM and the add-on module concept for concrete structure design within our programs. Then we'll immediately move on to our example, which is a concrete dome. We will fully model and load the structure according to the ASCE 7 in our main program RFEM. Here we'll run an analysis and take a look at the results. With these results, perhaps we could take them into our own in-house tools such as spreadsheets or whatever else to do the further reinforcement design. But today we're going to utilize the add-on modules within RFEM to do ACI 318 reinforcement design, and today we'll be utilizing RF concrete surfaces. Now this add-on module allows us to run both strength and serviceability design, and I want to show you how to both automated and manual input of the reinforcement areas. Lastly, we'll take a look at deflection with considerations to creep and shrinkage with the module extension RF concrete deflect. So to quickly explain RFEM and the add-on modules for concrete design, RFEM is our main program. This is where we're going to be modeling, loading the structure, and running a full analysis. As I mentioned, the analysis results could then be taken into our own tools that we have. But regardless, we can always utilize the add-on modules within RFEM for concrete design. Now, there is an umbrella term, RF concrete, to represent two add-on modules within RFEM. The first is RF concrete surfaces. This allows us to run both a strength and serviceability limit state design per the ACI, the CSA, many other international standards for surface elements within the program. The other add-on module, RF concrete members, also performs strength and serviceability limit state design per the ACI CSA international standards, but it also runs a deflection analysis. So we can take a look at deflection ratios based on the limiting deflection ratios that we put in. The module extension RF concrete deflect. So RF concrete surfaces is required in order to run this module extension. This performs an analytical deflection analysis in either the cracked or uncracked state. We can take into account creep and shrinkage as well. So we'll definitely be touching on this a little bit later on today. The last module, RF concrete nonlinear, this runs a nonlinear calculation for the serviceability state only in the cracked state. So we can take into account the true crack sectional properties for both surfaces and members. Again, this is a module extension. And with that said, we can jump into RFEM for our example today. So when we go to create a new model, we first want to give it a model name. Doesn't matter here, I called this one Webinar Dome. The type of model will be 3D. Now we can generate load cases and combinations automatically according to the ASCE 716. You'll notice here we have the NBC 2015 as well as many other international standards. Now with this checkbox checked, we'll automatically generate those load combinations. We can always uncheck this, which is standard, will be ignored, and you can manually create those load combinations instead. So once we click OK, we will be brought into RFEM. So you can see here we have our graphical interface in the center. We also have our tables to work with down at the bottom. You'll see a import and export button directly to Microsoft Excel. So perhaps you have all of your geometry modeled in Excel spreadsheets. You can directly import those in at the click of a button. Now we have our tools up at the top, which we'll certainly be utilizing today. And lastly, we have our project navigator over here on the left. Now the project navigator will allow us to access our input data. if we would like to make any changes, and you'll begin to see this generate as we create the model here in our graphical window. Our add-on modules are available here in a list. And lastly, once we do run an analysis, our results will also be available in this project navigator. So to begin with, I'm going to rotate the model around here. And I want to start off with creating a node. Now I can use this option up here, new node. I can either snap to a point directly in the graphical window, or I can simply type in the coordinates here at 0, 0, 50. So now you should see, if we right click out up here, my node, whoops, I didn't click enter, let me try that again. We'll type in 0, 0, 50, hit the enter key, there we go, we right click, and now that node will be generated within our window. So I'm going to move on to a line element. Now a line element is exactly what you would think it'd be, something similar to what you would use in AutoCAD. Now in addition to a straight line, we have many other features here that are similar to AutoCAD, such as circles, ellipses, polylines, arcs. For today we're going to utilize this option in arc where we define our radius. So with this, I'm going to zoom in here, and I'm going to click on my first point 50 feet away from the origin and snap to that second node that we just created. So now you can see here that I can go ahead and either snap to a point to define the radius of my arc, or just type in 50 feet, hit enter, and now we have that arc element created. I'm going to select this arc, and I'm going to use my rotate copy tool. I'm going to create 4 copies here with an angle of 90 degrees. Now we're going to rotate it about the origin, nothing too special here. But there is a setting called Edit Expanded Settings, and we have the option within this dialog box to actually create surfaces between my copy nodes. So what happens with this checked? Well, once I click OK through all of these dialog boxes, you'll notice that my dome roof was created with just a few clicks of a button. So the dome roof right now is bright red. That usually tells you that there's something that hasn't been defined within the model. So when I highlight all of my surface elements, I double click to edit them. We want to set the material, the thickness, and the stiffness here. Right now everything's set to null. So we're going to change this to standard. We're going to utilize one of the default materials within the program. So concrete 4000 PSI. Now you can always access your material library here to change the material or to create one yourself. The thickness of our dome walls will be 8 inches, and I click OK. So once I click out of here, you'll notice that the color is now gray, which is representative of our concrete material. So perhaps a weak point of a dome would be up here at the top, and we would want to add in some type of rib members for additional stiffness up at the top center point here. So I want to show you some of the useful features and tools that we have within RFEM to quickly do this. Now I'm going to turn this into a wireframe view, turn off my grid down at the bottom, and my line elements up at the top, I'm going to use my selection box here. I'm going to right click to edit the line. And under this option, we have Create Node on Line at a certain distance. So with this option, I can create a node on that line 10 feet from the line end. And you'll notice these black arrows back within RFEM show me exactly where the line start and the line end is. I click OK, so now I've done nothing more but just create little nodes here at the top of the dome. Now we're going to do the same thing at the bottom lines. I'm going to highlight all of these lines down at the bottom. Right click, and under line we can create a node on the line at a certain distance, again 10 feet from the line end. I do the same process again. This time I'm going to create the node on the line 10 feet from the line start. Okay, so all I've done here is add in these additional nodes to my structure. Now I'm going to utilize the line element again. This time with my arc, I'm going to choose the option here to define the arc with 3 nodes. So once I select this option, I can move this dialog box over, and I'm going to snap to these nodes that I just generated. So now you'll notice that I'm getting arc elements that match the curvature of my dome roof perfectly. So there aren't any additional definitions that I need to define here in terms of the geometry, but yet the program will automatically do it for us. Okay, so once I have done that, I am going to use this tool up here at the top, Connect Lines or Members. What this allows me to do is to highlight the top of my structure here. And now all lines that are intersecting will now be divided. And you'll notice that an additional node was created here at these intersections. So these are now separate line elements. I'm going to select 2 of the arcs over here, 2 on the back side, and I'm going to right click to reverse the line orientation. So now you'll notice when I select the other 4 arc lines that all 4 of these lines begin at the bottom of my dome structure and end at the top. So with this option, I'm going to right click and I'm going to divide the line this time by a certain distance. So from the line end, I'm going to divide it at 10 feet. I click enter. So now you'll notice I have a couple smaller line segments here. Well, now we're ready to clean up the model a bit. So what I can do is turn this into elevation view, highlight some of these unnecessary lines, and simply hit delete on my keyboard. We're going to do so on the other side after I've rotated the structure around. So now you can see we have these what will be rib members, but right now they're only lines. Now, before assigning a cross-section to these lines, what I need to do is to integrate these lines into each surface. So when I take a look at the rendered view, typically RFEM will do a lot of this for us automatically, but this geometry is a little bit more complex, and we added these lines in after the fact. So what I can do is to double-click on this surface, and we have a nice tab here called Integrated. Well, with Integrated, I can graphically select the lines, move this dialog box here, that I would like to integrate into that particular surface. So I click OK, and then I'm going to rotate around, do the same thing for my second surface, select my 4 lines graphically, click OK. We're going to do the same thing for the third surface, selecting the 4 lines, and lastly we have our 4th surface that we need to consider. So once we fully integrate these lines in here, the surface will recognize that these lines are a fully part of this particular 2D element, and I click OK. So turning this back into wireframe view, I'm going to zoom out and we'll put this into plan view. I'm going to hold down my control key and I'm going to select all of these line elements here. I'm going to go ahead and click on, oops, sorry, I lost that selection. Let's try that again. So I'm going to select these 4 line elements on each surface that we just integrated. And I'm going to right click on these lines to edit them. Now each member, such as a column, a beam, anything else, is comprised of a line element underneath it. All that we've done is assigned a cross section to create that member to each line. So we have a member tab here. With this member tab, we can simply select that a cross section is available, and automatically a new member dialog box will pop up. Now the member type is going to be the type rib. So what is so special about a rib element? Well, if I go into the detail settings here, you'll notice that a rib element can actually be placed below the surface. So the program will automatically determine which rib element should be dropped down below the thickness of that surface and do everything automatically. Even further, we can define an effective width for the rib member on either the left or the right side. So that will be taken into account later on if we wanted to do reinforcement design for this rib in one of our add-on modules. I click OK. I do need to assign a cross-section. So for this, I go into my cross-section library. We're focusing on concrete today, so here are all of my parametric massive sections. And in particular, we'll utilize this rectangle, and I just simply type in my geometric properties of 10 inches by 18 inches. F'(C) of 4000 is great. We will stick with that. I click OK through all of these dialog boxes. Now in wireframe view, it doesn't look like anything happens, but if we turn this into a rendered view, well, now we can see these curved beam elements drop below the thickness of the surface, and everything was done automatically. So very powerful modeling features here in order to model those rib members. So we're complete with the dome roof, and we want to move on to the lower wall. So for this, all I need to do is to highlight my line elements at the bottom. It's as easy as right-clicking on the line, extruding the line into a surface. So for this, I'm going to specify a wall height of 15 feet. The thickness of the wall is going to be 10 inches. In the global Z direction, I'm going to extrude these surfaces and then I assign my material to it. I click apply, and as easy as that, our walls are now modeled. Moving on to supporting the structure. So for this, we have nodal supports, line supports, and surface supports. For the bottom of our walls, we want to apply a line support. So we have a couple default options here, either hinged or rigid. Now we can always create our new definition, which you'll notice we have the 6 degrees of freedom, both translation and rotation. We have partial fixity, so if you have something that's not fully fixed, not fully released, but somewhere in the between, then you can specify a spring constant here. And lastly, because RFEM is a nonlinear analysis program, we can take into account geometric nonlinearities with these wall supports, such as sliding, friction, partial activity, maybe we have a failure. All of that is possible within the program. As for today, we will stick with the default of fully rigid. I click OK, and I just simply highlight the bottom line elements of my walls. Now this fully fixed support would be applied at every FE mesh point at the bottom of the wall. Okay, so now we are completely done with the geometry. There are a few considerations that I want to discuss before we move on to loading. Number one are our local axes of our surfaces. So for this, if we right-click to turn on the local axis system, you'll notice that my local axes are not all in the same direction, and this is a problem for 2 reasons. Number one, for loading considerations. If we were to apply loads according to the local axes, which we will do in just a minute, this can be a problem when we're trying to apply that load to multiple surfaces at once. Now the other and more important problem is our results. Our results will not be displayed graphically correctly if we do not orient these axes all in the same direction. Our results are going to be based on our local axes. So again, I'll mention this when we get to it, but point being that all of these local axes need to be facing in the same direction. Well, we have a nice feature within the program that all I need to do is to highlight this entire model. I right-click to edit my surface, and we have a tab called Axes here. This allows me to orient all of my axes at one time. So what I'd like to do actually before doing this is to take a look at the model. Now this line here, I'm going to right-click and I'm going to reverse the line orientation. So it's starting from the bottom and going up to the top. So now when I right-click to change the axes, I'm going to orient all of my local y-axes parallel to a line in the model. And I choose that line in the model, this one that I just reversed the orientation. So I click OK, and now you'll notice that all of my y-axes are facing in the vertical direction. Even the ones that have curvature up in our dome roof are facing directly towards the internal center point here. So that's one quick way that we can orient all those axes. So again, incredibly important. So let's turn off our local axis system and to move on to eye crack factors. Now the ACI specifies that we must apply eye crack factors to different components in order to modify the stiffness for our analysis for cracking considerations. So what we can do is once again highlight the entire model, we right click, and under surface we have edit, we have a modify stiffness tab. Now the default is always set to none. But when we use this drop down, you'll notice we have both ACI and CSA. When I take a look at the ACI, we have our different component types consisting of columns, walls, beams, flat plates, and flat slabs. When I choose walls uncracked, for example, well, this is the eye crack factor directly from the ACI code. Here's our reference that will be applied to this particular stiffness when we run our analysis. So I can click OK to modify the stiffness. Now, don't forget that we have these rib members up at the top that we need to do the same thing. When I right-click to edit the member, we also have a Modify Stiffness tab, and we can set the definition type according to the ACI. This time we will choose beams, and here's my eye crack factor that will apply to the stiffnesses for my analysis. And I click OK. Now, the final consideration is our FE mesh. Under Calculate, Generate, or FE Mesh Settings, you'll notice that these settings are set to 1 foot by default. Now, 1 foot is typically okay, But for a model this size, remember our diameter is 100 feet. Maybe we could go with something a little bit bigger. Now, this is a very happy medium that you have to find as the user. If we set something too large for the Femesh, then you're going to get inaccurate results. You set something too small, well, your results will certainly be accurate, but it may take you quite a while to solve your model. So for us today, I've determined that 3 feet is okay, and I can regenerate the Femesh upon okay. And now you'll notice that my Femesh is generated with the click of a button. Everything is tied into the nodes, to the lines, to the members, to the supports. I don't have to do anything manually. We can even put in Femesh refinements if we'd like to. Now, you don't even have to generate the Femesh. This will automatically be done every time we go to run an analysis, but I just wanted to show you here what that Femesh may look like. Okay, we are now ready to move on to loading. So for this, I'm going to generate new load cases, and you can see this tool up here in the toolbar, which opens up our dialog box. Now for our first load case, we're going to call this one dead, or we'll just call it dead, and we're going to assign the action category of dead here. Action categories are important so that the program knows which load factors according to the ASCE 7 to apply to which load cases. So for dead load, you'll notice self-weight is automatically checked here, so we will account for self-weight automatically. Creating a second load case, we'll call this one live 1. The action category will be live. We can make a copy of this one. We'll rename it to live 2. Creating a fourth load case such as snow with the action category of snow, and lastly 1 for wind with the action category of wind. Now keep in mind for all these additional load cases, self-weight is unchecked here. We don't want to account for it twice, so it's only active in the dead load. Under combination expressions, the program will automatically generate the LRFD load combinations and the ASC load combinations according to the ASCE 7. Now, probably most important is to view these load combinations listed here. So here are all of my LRFD load combinations, and here are my ASD load combinations. Now, these load combinations are only relevant for the load cases that I defined on that first tab. The results combination is going to be nothing more than an envelope solution to show you the max and min results. So we have an envelope solution or result combination for all of our LRFD load combinations and one for our ASD load combination. So that's something to keep in mind when we look at our results later. So once I've defined my load cases and combinations, you'll notice they're now available within this drop-down box. What we want to do is to make sure that we have the load case selected here of what we want to apply our further load. Now for dead load, I'm going to assume that I only want to apply self-weight here. So we're going to forego any additional loads for dead weight for now. I'm going to move on to live load. So for live load, we want to assume that this dome structure will be filled with some sort of material or fluid or whatever else inside, creating an outward pressure. For today, I'm going to assume that that outward pressure, that material, is only filled up to the top of my walls. So what we would like to do is to create a new surface load, and that is one of the other tools up here in the toolbar. So when I go to generate my new surface load, I am going to apply this in the local Z direction. Again, this is why local axes are very important to make sure they are all aligning. We're going to vary this linear in the Z direction. Now at the top of my wall, I want to have a magnitude of -2 kips per square foot. But at the bottom, I'd like to have -2.5 kips per square foot. So that's great. I've defined these two magnitudes, but I need to tell the program what is the top and what is the bottom of the wall. So I can graphically select 2 points. Here's the top of the wall, here's the bottom of the wall. So now those nodes are associated with those particular magnitudes. I click OK, and now you'll see that all I need to do is to select the bottom of my walls, and now that outward pressure is displayed. It has increasing magnitude as we increase in the depth of our wall. For live load 2, same concept, but this time I would like it to be some type of friction load, only applied to the walls. So for this, we're going to go back to our surface load. This time we're going to apply it in the global Z direction. Now you could apply it in the local Y direction as well. It doesn't matter. This we will it will vary linearly in the z direction. The magnitude, though, will be negative 0.2 to negative 0.25, so much less. The settings are remembered last time for what's the top of the wall versus what's the bottom. I click OK, and now you'll notice I just select my walls here, and here is my friction load applied to them. For snow load, even simpler. I'm going to go back to my surface load once more. This time I'm going to apply it in the projected z direction. So what does this mean? Well, at a point way out here on our dome roof, we're probably going to have very little snow load, if any. But at a point right here in the center where it's relatively flat, well, we want to see the full snow load. So with the projected load, it can take into account the different angles here of our dome roof. I'm going to change this to a uniform load, and the magnitude will be negative 0.03 kips per square foot. I click OK. I highlight the top of my dome surfaces, and there is my snow load applied. Moving on to wind load, and by far our most interesting load case. I am going to jump back to the PowerPoint for this to discuss a little bit about ASCE 7 2016 wind loads on domes. So within the standard, there is table 29.1-2. These are steps to determine the wind loads according to the main wind force resisting system for circular bins, silos, and tanks. This is incredibly user-friendly. It has all of the steps laid out for us on the assumptions that we need to make, the factors that we need to calculate, and ultimately to determine down here the wind force F or pressure P for both our walls and our roof. Now, for the sake of time, unfortunately, I can't go through all of this today, but I did make some assumptions for my structure, such as risk category of 1. My basic wind speed was 103 miles per hour. We're assuming the structure is somewhere in Pennsylvania. The exposure category is D, so maybe we don't have a lot of structure surrounding the area and we have these high winds. And I went ahead and calculated all of these factors to eventually determine that according to equation 29.41, which is referenced down here for my walls, here is the equation listed. Now, I moved my projected area to the other side of the equation. So what I wanted to see was my total pressure that needs to be applied to my wall. And what I came up with my calculations is around 16 pounds per square foot. Now, that's the total pressure. The dome roof is a little bit more complicated. Again, this is referencing equation 29.4-4 from step 8 here. And this in turn references us to figure 27.3-2 for dome roofs. Now this is actually adopted from the Eurocode and was only available within the ASCE 7 within the last couple of releases. So dome roof loads, we need to first consider the wind direction, of course, and then we have some various points here where our magnitude will vary. We have points A, B, and C. Now, the external pressure coefficients, the code allows us to interpolate, and all of these interpolations are based on the geometry of our dome. For example, the roof height, the wall height, the diameter, which we'll find the appropriate values here within this figure, and you can see my colored lines where I have interpolated based on our dome today. Now, eventually we get two load cases for A, B, and C pressure, as I mentioned, on the dome roof. And we get a second case for A, B, and C too, with slightly different pressures. Now, of course, we'd want to go through and maybe consider a different wind direction. If you have an asymmetrical structure, maybe we need to consider some torsional effects and so on. Again, for the sake of time, I'm only going to focus on this first case here and how we can apply it within RFEM. So jumping back to the model, the first thing we would like to focus on is the wind loads on the walls. I'm going to turn back on my drawing grid to assist me here, and I'm going to adjust the origin of the grid utilizing this button up here in my toolbar to move that to the front of the structure. So now, taking a look at the wind loads on the walls, I want to apply a free rectangular load. Now, a free rectangular load allows me to define a rectangular area, and all surfaces that fall within this rectangular area, well, this load will be applied to it. So you can see it's projected through that rectangular area to all surfaces within that box. So the first thing I want to do is to select my surfaces that this should apply to. Well, this only applies to my walls to begin with. I click OK. I do want to apply it, let's see, in the YZ plane here, and I want it to be a uniform load. What I'm going to do is I'm going to take that 16 PSF from the PowerPoint, I'm going to divide it in half. So 8 PSF on the front of the structure, 8 PSF on the back for a total force or pressure of 16 PSF. So negative 0.008 kips per square foot. And what I would like to do is apply it in the projected X direction. Now I need to define my load position. So for this, I just need to click 2 points here for my rectangle. So what I'm going to do is I'm going to turn this into elevation view. I'm going to snap down to the bottom of my walls, negative 15 feet. And then as far as the second point, I'm going up to the top of the wall. And just like that, my points are automatically shown here within the program. So this will make a little bit more sense once I click OK. Now we take a look at these wind loads. It is in the projected X direction only being applied to these walls. Now once we run an analysis, we'll show you the load distribution on the structure, which will make even more sense. But for now, we'll move on to our roof. So I'm going to select only my roof members here just to create an easier visibility by selected objects. And once again, I'm going to create a new free rectangular load. Now for this, I'm going to only apply this to the front 2 surfaces to begin with. I click OK. And the plane is going to be in the XY plane. The direction is going to be in the local Z direction. Wind pressures are going to be applied normal to the surface here. It is going to vary linearly in the X direction. Now remember from the PowerPoint, at the front of the structure, point A, this should be 0.016, so 16 pounds per square foot. At the top of the structure, point B here, we want this to be negative 0.041. This is suction load. So again, this was all taken from the ASCE7 calculations that I had done from the PowerPoint. I'm going to select my load position again. This time we select a rectangular section here that encompasses those front 2 surfaces. So I actually will change this to 50 feet. We can manually change it here as well. I click OK. So now when I take a look at the pressures applied to the front 2 faces of my dome, here is my 16 PSF at the front. Here is my 41 PSF of suction up at the top, and it is displayed quite nicely. Now as for the back of the structure, same exact concept, and a really easy tool to use is to highlight this rectangular load. Well, if I can select it. Okay, let's highlight this free rectangular load, and then I'm going to use my Move Copy tool. I'm going to create one copy, and I'm going to apply it in the negative 50 foot direction according to my global x-axis. Now I want to clear off the create surfaces between copied lines. So I click OK, and now that free rectangular load was applied to the back of the structure, but we need to make some modifications according to the pressure. So let me go back to creating a visibility by selected objects. I'm going to double click on this free load in the back. Now this is not applying to surfaces in the front, but rather only the 2 surfaces within the back. So I graphically select them, and I want to adjust the magnitude here. That's the only thing I need to do. So at the top, point B will be negative 0.041, and at the back side will be negative 0.011. And I click OK. So now my pressure is adjusted accordingly. Now this matches up perfectly to my points A, B, and C that I determined from the PowerPoint. So point being that we have so many features within RFEM that allow us to do these crazy wind loads on specialty structures, on not straightforward buildings, but rather curved domes and such, as you see here. Okay, so once we have completed all of our loading, maybe we want to scroll through some of these load combinations to take a look at all of them acting together. You'll notice here, for example, we have wind load, live load, snow load, dead load, all acting together. And now we're finally ready to run our calculation. So we can go to calculate, calculate all, and this does take a split second to run. So what I'm going to do is to go to an already saved model. And when we run our analysis, we're immediately presented with something that looks similar to this, showing us our global deformations. Now, here's the results available in our project navigator for the particular load case of dead. The thing I want to jump down to before getting into the analysis is the distribution of load. Now, in particular, I'm going to scroll to my wind load here, and I'm going to view it according to my 2D surface elements in the local Z direction. So creating a visibility only for my dome, I create that visibility. Let's take a look at the distribution of the load. At the front, we have our 16 PSF. At the top, we have our 41 PSF of pressure, and at the back, we have approximately 11 PSF, of suction for both the top and the back. Again, this just comes directly from our PowerPoint. So I've also went ahead and added in some sections here. And these sections, which I can turn on, just simply make a cut right through the center of our model. So looking at our sections, we can see here that the 16 PSF, 40 or 41 approximately, and 11 PSF apply to the structure. Now when we rotate this to a point that is perpendicular to the wind load, we should see approximately the same magnitude everywhere. And that is what we see, approximately 40 pounds per square foot of suction. Now the same goes for any point perpendicular to the wind load. So that is great for the distribution of load. Maybe we want to move on to the rest of the structure here. Well, what we're first going to be presented with is our deformations, and we can scroll through our various load cases and combinations. You'll notice that these sections are still applicable for any results that we're looking at, so that just makes that section cut to view that easier. Now remember that we have our members up at the top too, so turning off my sections, we have these internal forces for our members, for axial loads, for example, shear forces, moments. So we can take these internal forces into our own tools, whatever we have in-house, if we wanted to do further reinforcement design. Now for today, we are focusing on our surfaces. So with our surfaces, you can see all of the information available here, such as MX, MY. Again, we can turn back on these sections here to view a cut through those. And keep in mind, like I said, these results are based on the surface's local axes. Again, why it is so important to make sure all of your surfaces are oriented in the same direction. We can view stresses, we can view strains, all graphically here. So that's pretty much in summary what I wanted to show you that RFEM is comprised of for the analysis portion. Now for us today, we want to move on to design utilizing the add-on modules. So for this, I'm going to jump back to my other model here that we're working on, and I am going to launch RF concrete surfaces. So the add-on module is nothing more than a dialog box. All of our loading, our load cases, combinations, materials, thicknesses, everything is brought in from RFEM into this add-on module. The only thing I have to do is to specify some information that is relevant for design, reinforcement design, per the ACI. So you can see here we have both the ACI and the CSA available. We'll choose ACI for today. Now the strength limit state, I'm going to choose all of my LRFD load combinations selected for design. Serviceability, I am going to select all of my ASC load combinations selected for design. Here is my first case. What we could do is go to File, Rename Case. We could call this one Strength and Service, just to be clear on what we're designing for here, and then I just simply move down my list. Materials are brought in from RFEM. For both concrete, reinforcing steel is set here as well. Now you can use this drop down to make adjustments that you would like. You'll see the material properties are also listed here. Surfaces, again, all of the surfaces are listed. Now, everything is synced up to RFEM in the background. So as I'm clicking through these tables, you'll notice that it's highlighted in the background exactly which surface I'm looking at. Now, something to note for serviceability design, that we can design for crack width. So this option is only available because I had defined these serviceability load combinations. And for crack widths, we want to first give the program a limiting value. So the first option here, limit values, has our drop-down box, which comes from the ACI committee. They gave us some allowable crack widths based on the exposure conditions of our structure. We will assume today that the structure is in a very humid environment, so our allowable crack width is 0.012 inches for both the top and the bottom. You can also use a user-defined option here to type that in manually. We have two different checkboxes here, design without direct crack width calculation according to Chapter 24. Well, the ACI doesn't necessarily have limiting crack width values. What it does have is requirements for reinforcement spacing to make sure that we don't have any cracking issues. So with this checkbox checked, we will double check the spacing of the reinforcement to make sure we're meeting all of those minimums or maximums. The other option is design according to direct crack width calculation. This will apply a theoretical calculation. It's the Gurgley-Lutz equation. We will calculate a crack width based on the applied loads for our structure. Then we will compare that to the limiting value here to eventually get a serviceability design ratio. Moving on to reinforcement. The first thing we want to do is to create two separate reinforcement groups. The first one will be dome. And I don't want to apply this to all surfaces, but rather I'm going to graphically select my dome roof. I click OK, so it's surfaces 1 through 4. Now we have some reinforcement minimums here. You can change these as you see fit for your particular project, in particular maximum reinforcement percentage. This allows us to avoid brittle flexural behavior. The default is set at 9%, but you can adjust that as you see fit. The reinforcement layout, this is where we define our concrete cover. It can either be measured from the centroid of reinforcement or to the edge of reinforcement. For today, I'm going to specify this as 2 inches in both directions for both my basic reinforcement and my additional reinforcement top and bottom. The longitudinal reinforcement. So for this is my provided basic reinforcement. For my dome, I'm going to make the assumption that number 6s at 12s is going to be perfectly adequate based on these applied loads. So what I'm going to do is to utilize this nice tool that we have here. Now, assuming number 6 is at 12 inches, my diameter is 0.75 inches, and my spacing is 12. So when I click OK after applying it to both the top and bottom and both directions, my reinforcement area is automatically calculated here along with my diameter. This second option, additional reinforcement for serviceability state design, well, there's 3 options here. And the 3 options are laid out a little bit better in this little info button. So with this info button, we can see that the first 2 options will increase my longitudinal reinforcement as the program sees required. Instead, I'm going to choose this third option down here. I don't want the program to automatically increase my reinforcement, but instead I want to define what additional reinforcement I should put in here. And for right now, I'm going to leave this as 0. Again, I'm assuming these number 6s at 12 inches are perfectly adequate. So moving on to the ACI 318 tab, there are some minimum reinforcements here according to plates for Chapter 9. I'm going to uncheck this, and instead I'm going to use the minimum reinforcement for walls according to Chapter 11. We also have shear reinforcements, shear strengths that all come directly from the code. If you don't see these minimums as fit for your particular structure, maybe you're not following the ACI for these provisions, you can just simply uncheck them. These strength reduction factors, for all of us who have done concrete design, we know that these come directly from the standard, Chapter 21. These default values in here do come from the ACI, but you can override them if you choose to do so. Lastly, the design method. We have two options here, no optimization for our internal forces or optimization. Now the important part is just to read between the parentheses here. So this is recommended for parts mostly loaded by pressure. This is recommended for parts by bending or tension. So we will leave this optimized for now. So essentially we are done with the reinforcement provisions for our domes. Now what I would like to do is to simply make a copy of this reinforcement group. I make that copy and I call this one walls. So now you can see both reinforcement groups are available over on the left, or I can use my drop down available here. The program automatically assumes that surfaces 5 through 8 should be applied here. That's correct, but I can also graphically select them as well. The only thing that I'd like to do different is instead of number 6s at 12s, I know I need an increased reinforcement here. So instead, I am going to choose number 7s at 8. My diameter for number 7s is 0.875 inches and my spacing is 8 inches applied to the top and bottom in both directions. I click OK and now you'll see that increased reinforcement area listed here. Absolutely everything else is unchanged from what I just set it to because I made a copy of that reinforcement group for my dome. So now we're ready to run our calculation. Now, again, this takes just a couple minutes to run, so I'm going to jump to our already saved model. And what you should see when you run a calculation is you will automatically be jump to this table here. You'll see our results table available after you run that calculation. So the required reinforcement by surface. We will see in here 4 different columns. So the required reinforcement is what the program has determined for all of our reinforcement directions, top, bottom, required by analysis. My basic reinforcement is what I put in there. So remember my number 6s at 12s for my dome and my number 7s at 8 inches for my walls. Now there is an additional required reinforcement area. If I am seeing numbers here, that usually means there is a problem. My basic reinforcement that I just put in is less than my required reinforcement. Now, these tables are nice. Keep in mind that they are all synced up here to the background within RFEM as we scroll through them, so you can see exactly where the controlling internal force is. But let's actually jump to the graphics view. So we're still technically in the add-on module. You can see this from the drop-down box here in our panel, but we're viewing the results back in RFEM. So what I want to show you is, number 1, the required reinforcement. So this is what the program has determined that it needs to have based on the applied loads. Here are my 4 different longitudinal reinforcements. So you can see here I have both top and bottom in one direction and top and bottom in the second direction. If we zoom in, we can see the reinforcement layout direction graphically displayed as well. So that's great, but what have I provided? Well, provided basic reinforcement is listed. Here are my number 6s at 12 inches and here are my number 7s at 8 inches. So this is what I have input into the program. So now the important part is to jump to this ratio, AS required over AS provided. Anything greater than 1.0 here is a problem. Again, this means that my required reinforcement is greater than what I have told the program to actually put in there. So you'll notice that for all of these different reinforcement directions, top and bottom, we have some ratios greater than 1.0. Even more helpful is to view the not covered reinforcement. This is my AS required minus my AS provided. This is what I still need to put into the structure in order to pass the design requirements. So we can scroll through the different options here and you can see exactly where the problem areas are that I just simply don't have enough reinforcement. So what I went ahead and did is, back in the add-on module, I went to File, Copy Case. And when I copied the case, I created a different name for it. And all of my settings were remembered from my first case. The only thing that I did was jump to my longitudinal reinforcement and I increased my area here. For my dome, I'm now looking at number 7s at 8 inches. That's all I've done is increase the area. For my walls, I've increased the area to number 10s at 8 inches, so significantly more reinforcement. Now, once I run my calculation, I'm immediately brought into my results table here. So now we can see that this additional required reinforcement, it's all 0. That tells me that the program has met the necessary reinforcement requirements just based on what I put in there. If I jump back to my graphics view, required reinforcement is still the same. Nothing has been altered here because I haven't adjusted any of my applied loads or the structure itself. And as far as the provided basic reinforcement, this is now increased. So when I look at my not covered reinforcement, this is any reinforcement that is still required, you'll notice that everything is zeroed out. That means that my provided reinforcement is adequate for this design. So that's how we can add the reinforcement to the surfaces individually. What I would like to show you now is that ideally, especially for a structure this big or any structure in general, we're probably going to optimize the reinforcement, meaning we're going to put more reinforcement where it's needed and less where maybe we don't need as high of reinforcement. So how can we manually define where to put these different reinforcement areas? Well, for this, I'm going to jump back to my webinar that I was currently working on. And we're going to launch the RF Concrete Surfaces module. I'm going to go to File. I'm going to go to New Case, or sorry, Copy Case. And this one we will call Strength and Service Manual because I'm going to manually apply those reinforcement areas. I click OK. So once again, nothing has changed here because I made a copy of that case. So really beneficial not having to re-enter in all that information. The difference here is I'm going to launch this Details tab. So under the Details, we have two options here, to automatically arrange our reinforcement or to manually define it. And this is where I'm going to choose the option Manual Definition. I'm going to click OK. Now you'll notice that this dialog box looks slightly different. This is the only part that is affected in the module by changing that to manually. For my domes, I still have my reinforcement area for provided basic reinforcement. I am going to open up my little tool here, and I'm going to assume that for this particular reinforcement, I want number 10s, which is a diameter of 1.27 at 8 inches. I'm going to apply this to the top, bottom, and both directions and click OK. So you can see my total reinforcement area is shown here. Now I'm not going to do anything further with my dome. I'm going to assume I do want these number 10s at 8 inches. Oh, I'm sorry. Actually, that's entirely too much reinforcement. Let's go back. We would like to apply number 7s at 6 inches. So we will go with a diameter of 0.875 and a spacing of 6 inches, top, bottom, and both directions. Okay, so now we're looking at a reinforcement area given here. I'm assuming that I want those number 7s at 6 inches everywhere within my dome roof. So we're not making any changes here. Now, for the walls, though, I do want to specify two different reinforcement areas. At the top of my wall, I want a higher reinforcement. At the bottom of my wall, I want a lower reinforcement because it's not needed there. So the first thing I'm going to do is I'm going to zero out my provided reinforcement. We can put something here if we'd like, but for right now, I'm just going to zero this all out. The provided additional reinforcement can be placed in several different shapes here. For example, we can apply additional reinforcement for a particular surface. For a rectangular area, again, this is going to be a rectangular area projected through several surfaces. A polygonal area, which is what we'll be utilizing today, or a circular reinforcement area. Circular might be incredibly beneficial for the top of our dome here if we wanted a different reinforcement in a circular fashion. So really any shape is possible. Utilizing the polygonal reinforcement, what I'd like to do is to launch this dialog box. So for this option, I want to apply this in the YZ plane. And you'll notice that this is applied to surfaces 5 through 8, which is pulled directly from my walls. I can always adjust this if I'd like to do so. I'm going to apply as top, bottom, and my first direction. The rebar for the top of my walls, I want this to be number 10s, 1.27 diameter, at 8 inches. Now, this will typically be blank when you first pull up this dialog box, and I now need to define the reinforcement position. And this dialog box looks pretty similar to a rectangular freeload, so same kind of concept here. I'm going to graphically choose now, and I'm going to turn back on my grid. I'm going to rotate the model, and I'm going to snap to the points in elevation view where I want these number 10s at 8 inches to apply. So I'm going to move to the top of the wall all the way down to a point about 3 feet from the bottom of the wall. Moving to the other side, a point 3 feet from the bottom of the wall up to the top of the wall. Now once I click those 4 points, I right click to get back into this dialog box and I click OK. Opening up this same dialog box, all of my settings that I just put in are remembered. The only thing I'm going to do is change a direction and click OK. So now when I take a look at this table, you'll notice that I have my number 10s at 8 inches applied to both the top and bottom in both directions at these particular nodes. So they're projecting through my surfaces 5 through 8. So I click OK. Well, what about the bottom of the wall? Well, this is where I want to come in. And again, most of these settings remain unchanged. I go back to my direction 1. I want to decrease to number 9s. Maybe I don't need number 10s, but I want to decrease this to number 9s. So we'll choose a diameter of 1.128 at 8 inches. Now for this, I want to clear out this selection here, and I'm going to graphically choose the bottom 3 feet of my wall. So what I can do is just to turn this into elevation view, snap to a point at the bottom, snap to a point 3 feet from the top, move over to the other side 3 feet from the top and down to the bottom of the wall. I right click and my points are automatically populated here. Now I click OK. I open up that dialog box to change my reinforcement direction in the other direction here. I click OK, and now when I look at this table, I now have the bottom 3 feet of the wall with slightly less reinforcement. Now this table is nice, but it might be beneficial to see this graphically of how it's applied to our surfaces, so that's what this little eyeball allows us to do here. When we click on this, we are brought directly into RFEM, still with this table being displayed here. Maybe I turn on my color panel here. Well, now I can see that for the top of my wall, 1.9 inches squared per foot is applied, but at the bottom, I only have 1.5 inches squared per foot. And the same goes for all the way around the structure. So pretty beneficial for viewing visually what we're applying. So now that we are done with the reinforcement, I'm ready once again to run my calculation. So once again, jumping to my saved model, I would like to take a look at the results. So we are immediately brought into our required reinforcement here. And you'll notice that the required reinforcement is listed based on the analysis. Again, nothing should be changed with that. The basic reinforcement is also listed as well as additional required reinforcement and so forth. But like I said, most beneficial is probably to jump to the graphics view. So for the graphics view, we want to take a look at, again, required reinforcement did not change here. The provided basic reinforcement, remember I've only provided that for my dome surface elements here, 0.9 inches squared per foot. The walls are 0. Instead, for the walls, I define that as provided additional reinforcement. Here's my 1.9 inches squared at the top of the wall and 1.5 inches squared at the bottom. We can view everything added together for provided reinforcement. 0.9 inches squared per foot, 1.9 inches squared per foot, and 1.5 inches squared per foot. Now when we take a look at our not covered reinforcement, it looks like everything is 0. So based on the applied reinforcement that I put into the program, we are meeting what the required reinforcement is. So one thing I also wanted to mention quickly is our serviceability design. We haven't touched on that yet. So if we jump to the serviceability table, you'll notice here is my crack width. Here's my existing value based on the applied loads. Here's my limiting value. Remember, we set this as 0.012, and ultimately we get a ratio for our serviceability design. Gurgley-Lutz equation is listed here, and all the information necessary for that. We can also view our serviceability information graphically. For example, here's our serviceability tree. We can view the ratio for cracking back in RFEM. So the last and final thing I want to touch on is deflection. So going back to our working model here, we want to take a look at the add-on module, RF concrete surfaces, and I'm once again going to go to File, Copy Case. We will call this one Deflection. I click OK. Now I've made a copy of this case, so everything has already been defined for my reinforcement. I don't need to adjust anything. The only thing I want to show you is under serviceability limit state, we have two methods of check, analytical, nonlinear. Now nonlinear is for the module extension concrete nonlinear. We won't be getting into that today. But rather, when I go into the details here, we're already designing our serviceability for cracks, but we have another option here called deflection with RF concrete deflect. Now again, this is a module extension. When I click this option, the program throws up a warning saying we're not going to adjust the required reinforcement based on deflection design or deformation checks. That's fine. Basically, all we're doing is checking the deflections but not adjusting any reinforcement. Now, long-term deflection with considerations to creep and shrinkage can be considered here. Now, this all just comes from the ACI. The ACI requires maybe creep and shrinkage to be considered for uncertainties in temperature, humidity, curing conditions, and so forth. We can put in here the duration of our load. Now, in turn, this duration comes from table 242413. It affects our multiplier for long-term deflection. That multiplier will be multiplied by the immediate deflection, and that's what we'll be checking within this add-on module. Tension stiffening, with this check, this is just telling us that the concrete, in addition to the reinforcement, will contribute to the resistance of the internal tension forces. If I were to uncheck this, we're assuming that only the reinforcement will contribute to the resistance of those tension forces. So we will leave this checked for today. So I click OK. Now the only thing that's changed is under my Surfaces tab, we now have an additional tab here for deformation analysis. So we've already discussed crack widths, but right next to it is deformation analysis. Now we have some limiting deflection ratios here. So you can see here that we have either the minimum boundary line, the maximum boundary line, or we can select some type of user-defined relative distance. The default is L over 250, but you can override these as you see fit. Now, something that's useful is to launch this little info button. This tells you exactly what it means by minimum boundary line, maximum boundary line. Now, for today, we kind of have these odd surfaces, especially for our dome, where I broke apart some of the lines. So in my opinion, it's not ideal to use these today, but rather I'm just going to use this fourth option, and I'm going to say I want no deflection greater than 1 inch. So the next question is to determine the deflection that we're checking. Is this based on the undeformed system or the deformed system? This is simply absolute versus relative deflection. So the undeformed system is going to be absolute. It's going to be measured from the undeformed structure to the deformed structure. The second option here is maybe explained a little bit better in this picture. You'll notice that the deflection is simply measured from our deflected shape from corner point to corner point. The first option here is absolute deflection. For today, we'll utilize the undeformed system. So everything else remains unchanged. Remember, my reinforcement has already been defined, and I'm ready to run my calculation with deflection considerations. So for the last time today, jumping to my saved results, I want to take a look at my RF concrete surfaces module. The only difference we're going to see here is under serviceability design. We no longer just have the crack width considerations, but here is my deflection checks. My existing values are listed for each surface, and again, I can take a look at exactly where these fall within the structure in the background, if I pull this down a little bit, as well as the limiting design values. Remember, we just set this to 1 inch, and ultimately we get a deflection ratio. We can view all of this graphically as well under the serviceability. Now we have the option to view the deflection ratios back in RFEM. So that's really all that I wanted to touch on in regards to deflection as well. Okay, so going back to the PowerPoint, that essentially wraps up our webinar for today. Now, I know that was a lot of information, as it always is, for the last hour. We always want to encourage you to visit our website at dlubal.com to learn more about RFEM and these add-on modules that you saw. We have several social media sites. For example, our YouTube channel is incredibly beneficial to take a look at some of these recorded webinars and to view them at your own pleasure. Our email at our Philadelphia office is info@dlubal.com. Again, info@dlubal.com. The phone number is 267-702-2815. So if you have any questions about today's presentation or anything else, feel free to contact us here. As we continue to have more webinars, you can register for them under our website, Support and Learning and Webinars. Most of you know today I also send out a couple of reminder emails when those webinars are to occur, so keep your eyes peeled for those. Many of you are wanting PDH credit. That's great. What I do request is that you are here for the full presentation and you send an email to me at info-us@dlubal.com. So just simply let me know who was in attendance today and I will be happy to issue that certificate and I will email it back to you. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next webinar. Thank you.